Welcome. Today we're going to learn about Rolle's theorem. So what is Rolle's theorem? Well, first of all, we have three basic criteria we need to begin with. Number one, our function must be continuous on a closed interval AB. Second, the function must be differentiable on an open interval AB. And third, if f of a is equal to f of b, very important to set up that criteria, then at least one c in AB occurs such that the first derivative at c is equal to 0. Now I will leave it up to the book and proofs that I do in class to get through the proof of this particular theorem. Today we're going to focus on an example where we apply the theorem. So first of all, in 1 we have a function. We also have to the right of the function, you will see we've restricted our function to within -1 and 6, and the brackets indicate it's a closed interval. We are only looking within that particular portion of the x-axis when we look at this function. We're not looking at anything beyond -1 through 6. Okay, now, first of all, we said the first two criteria of the theorem was that our function must be continuous. Well, in this case it is. It's a polynomial and they're all continuous. The second thing is it has to be differentiable. Same thing, it's a polynomial, so it is differentiable. So we meet the first two criteria. In some cases, you may have a function that possibly has a discontinuity. Maybe if it's a fraction, you could have a denominator that is 0 at a point. You could have a situation in terms of differentiability if you have a graph that has a sharp turn or has a vertical tangent line at a particular location in the graph. Those are points where your graph would not be differentiable. We do not have any of those situations here, but I wanted to mention them because you may encounter this in other problems. Number 2, the next step is to set f of a equal to f of b. And you want to make sure that basically if you plug in the endpoints, in our case -1 and 6 of your interval, you plug them back into your function. In other words, you replace x with those values. You want to make sure that those y values are equal. In 3, this is exactly what we're going to do. First we plug in -1. So we replace all the x values in our function with -1. We get 0. We do the same with 6, and we also get 0. This is good news, because in step 4, we realize that they are clearly equal to one another, and we have verified that that occurred, and now we can move on with the rest of the theorem. Number 5, next we're going to set the first derivative equal to 0, and we have a basic power rule. We do that. We solve for x. You can see we attempt to do that in step 6, and we solve it in 7. And we find out that the c, remember we're looking for this c value between -1 and 6, where our first derivative of our function is 0. We find out it's 5/2 in this particular case. Now what does the graph look like? This is a graph of the function we just did. And you can see on the x-axis that I've highlighted the interval that we were looking at, -1 to 6. And if you look at the graph, you'll see at item 1, that we have a relative minimum. In other words, there's a value in our graph, and that is where we have a relative minimum. We also see it's a smooth curve, which means it's differentiable, and we can draw a horizontal tangent line to that curve, and that is where the first derivative of that curve would be 0. And guess what? If we follow up to the x-axis, we find out that that concurs with what we just found. The x value, where the first derivative of our function is 0, our c is 5/2, which we just analytically calculated. And that happens to occur within our interval. Now, that's Rolle's theorem. Now go practice, and practice some more.